All right, so the next talk will be by Aidan Herderschee, and he will tell us about flat space, Feynman integrals, and amplitudes. Sorry,
Can
that's
I
not
not
the
go
title.
back?
Well, you see that it's scheduled. So
Try now. Are you able to?
Oh, yeah, there we go.
all right, go ahead.
Hello, I would like to, I'm Aidan Herderschee. I'm a postdoc here at the IIS. I'm very honored that I was invited to speak. It's great that there are so many people here that we can talk about physics and amplitudes. Specifically, right now, I want to talk about a paper that I did with some of my collaborators, Mark, Radu, and Faye, who are great, on a paper that was posted last week on Witten diagrams and specifically how we can compute their difference equations in summation by parts. Thankfully, due to the talk before me, I think I can focus a little bit less on motivation than I would otherwise, because of a lot of the motivation that applied to the previous talk applies here, but so that's a little bit nice for me given the timing. So the story that I specifically want to focus on in flat space, which is what I want to generalize to curved space, is specifically focuses on Feynman integrals. So what's the story with Feynman integrals in flat space that I want to focus on? The first one is that if we have tree-level amplitudes are rational functions. When we go to loop level, we have non-trivial integrals. We have a variety of methods for computing those integrands. But then once we get to once we actually have the integrand, there are two standard tools that we have for actually computing the full amplitude. The first one is integration by parts, where we take the basis of functions and we reduce it to some much smaller finite basis. And then we find the differential equations that our Feynman integrals obey, and we just solve those differential equations using a variety of techniques, such as canonical differential equations. My goal of this talk is to take these two strategies, integration by parts and differential equations, and generalize them to one loop diagrams in ADS with generic masses for the internal and external states. So I want to go beyond flat space, specifically anti-de Sitter. So the previous talk talked a lot about why we should care about de Sitter. A lot of the strategies that I'm going to talk about I think should be applicable to de Sitter. But I focus on anti-de Sitter largely because there are a lot of examples available in the literature for loop-level Witten diagrams. And in general, I can, through ADS-CFT, by studying higher loop Witten diagrams, I'm actually indirectly studying strongly correlated, strongly coupled systems of a certain type. So what are the things that I'm computing? What is ADS? So ADS is a maximally symmetric space. It's like putting your system in a box. I've given a rough picture here where this red part of the diagram schematically corresponds to ADS. Generically, X is going to denote a bulk coordinate. P is going to denote a boundary coordinate. Bulk to boundary propagators are going to be denoted as E. Bulk to bulk propagators are going to be denoted as G. And mass is going to be delta, capital delta or small delta, which corresponds to the conformal dimension of the state on the boundary. Note that capital delta and small delta are basically interchangeable. They just differ by h, which is equal to d divided by 2. D corresponds to the space-time dimension of the boundary theory. So whenever you see d or h, that corresponds to boundary space-time dimension. So if you're thinking about the bulk picture, which I think most of us here do, then you should think d plus 1. So what are the things that we're actually computing? We're computing Witten diagrams. So this is the way that you compute boundary correlators in ADS. So I'm inserting some operators near the boundary, and I'm studying their correlation functions. And the way you do so is with Witten diagrams. So here with Witten diagrams are very similar to normal Feynman diagrams, except you draw this big circle around them. For every edge, you associate a propagator, and for each bulk vertex, you associate an integral. So here, there are 4 bulk to boundary edges here. 1 to this one, 2 here, 3, 4. So there are 4 bulk to boundary propagators here. There are 4 E's. And there's 1 bulk to bulk propagator G, GX1, GX2, which corresponds to this edge here. And then there are 2 vertices, X1 and X2, which correspond to due bulk coordinates over DX1 and DX2. So what's the problem with this picture? Well, and I said I focused it in flat space. At tree level, our amplitudes are rational functions. This breaks down in ADS and de Sitter. You have non-trivial to compute the correlation function even at tree level. You have to really do some non-trivial integrals. So there are already problems where there were no problems before doing the simplest kind of computation you can imagine. This is in a sense one of the simplest diagrams you can imagine and involves 2 d plus 1 dimensional integrals. And again, the propagators are generically not nice functions. So before, a lot of the time people restrict to conformally coupled scalars, so the propagators become simple. If you make the propagator, if you allow for generic masses, so not conformally coupled, and you work in ADS, the propagator is a 2f1 hypergeometric function. So when you go back to that S-channel Witten diagram, you're doing an integral over a 2f1 hypergeometric, doing a double integral over a 2f1 hypergeometric function. The bulk to boundary propagators are simpler, but there's already like a lot of complexity here. Then finally, in the case that we actually do have results, the results that we have usually turn out to be certain types of hypergeometric and digamma functions of the mass and dimension. Digamma functions do not really have nice differential equations in a sense. There's like Holder's theorem can be generalized to show this. So you're kind of, yeah, you already have problems. One solution which is what we're going to do in the remainder of this talk is that we're going to work in melon space. So melon space is kind of something like a momentum basis for ADS. It won't really matter until the very end of the talk if you don't know what it is. So the intuition here of this talk is that I've told you a lot about why ADS and de-Sitter are scary things to do. You have 2f1 hypergeometric functions. Hypergeometric functions are scary. You have many integrals over those hypergeometric functions. The functions that you get out are scary. They're digammas. They're hypergeometrics. They're not nice polylogs. So why do you have any hope of having computational simplicity? The intuition that I want to give you here is this idea that when you go to ADS, you're putting your system in a box. And what happens when you put your system in a box is that your spectrum becomes discrete. So in ADS, my spectrum is a continuum. In flat space, my spectrum is a continuum. In ADS, my spectrum becomes discrete. What might expect from this is that when you're doing like differential equations or integrals in flat space, in ADS, if you're doing the calculation in the correct way, that should really map to doing difference operators, because it's discrete, and sums, because again of discreteness. So this is this kind of intuition that it's not really hopeless if you use the correct language, if you do the computation in the correct way. It's just that a lot of your continuum integrals are now being replaced by sums. So to kind of illustrate this point in a cartoon, for those of you who won't follow the rest of the talk, I'm going to look at a 2-point bubble in d equals 2, which has been known for a while, and I'm going to reverse engineer the difference equation that it obeys. This is just to illustrate that this is the correct way that you should think about this. So this is the 2-point bubble. It's proportional to the sum of two digamma functions. As I said before, digamma functions don't really have that nice differential equations. I use nice in a very loose sense. This was derived in these two papers that were from almost 10 years ago now. And this looks like not a great thing. Like digamma functions are not particularly nice. They're not logs, which is what we have in flat space. However, digamma functions do obey a nice difference equation. So digamma x plus 1 minus digamma x equals 1 over x. This formula should look familiar. It's basically the ADS analog. It's the discrete analog of log x. What is the defining property of log x? That the derivative of log x equals 1 over x. So here, I'm telling you that digamma is the discrete analog of the log, because it has this property that if I take the difference equation of digamma, I get 1 over x. And this makes a lot of sense because the bubble in flat space is a log. So here, it's natural that in ADS, you would now get a digamma function. You can then take the function before for the 2-point bubble, that's digammas, and you can use the fact that the digamma obeys a nice difference equation to reverse engineer what difference equation the bubble should obey. And it's this really nice rational function here. And this is exactly analogous to the differential equation that you derive in flat space, except now it's a difference equation. This d here is a difference equation acting on this in delta 1. Now, you can tell me this is somewhat trivial because I haven't actually really done anything new. Like the 2-point bubble has been known for a while. Again, it's known for almost 10 years. And we knew the result beforehand. Really, the goal is to compute difference equations when we don't know the answer beforehand. This is the power of differential equations for Feynman integrals. For Feynman integrals, I can compute the differential equations algorithmically, given a generic Feynman integral without actually evaluating it. Now, converting that differential equation to a form that's actually tractable is an entirely separate matter. But just computing the differential equation itself that is valid is something that is algorithmic. And the goal is, how do you do this for ADS? How do I algorithmically compute the difference equations that an ADS diagram obeys? So as an example of a more non-trivial result, to flash this before I get to go back to simple examples, is the 4-point melon amplitude. So we take the 4-point melon amplitude. It's a function of s. This is kind of like momentum variable in ADS. It's like you've done a melon transform of your 4-point bubble. And this is the difference equation in a base with all the deltas equal to 2 and in space-time dimension d equals 2 on the boundary. This does not look very nice, but it's actually not that bad. It fits in 4 lines. It's human readable. I could memorize this. I wouldn't, but I could, maybe. And the point here is that we derived a difference equation. The 4-point bubble is not generically known. So it's known in this specific case here where all the deltas equals 2 and d equals 2, but it's not a generically known function. So we were able to derive the difference equation of a function we don't actually know. And what we did is that this function is actually known in this specific case. And what we did is that we checked the function obeys the difference equation. And this is what the difference equation reduces to when you set these values. And we checked that it was valid. So that should give you confidence that the strategy that I'm going to describe to you is actually correct. So again, the big question here, how do I compute the difference equations without knowing the answer? So how do I compute difference equations without actually doing the final result? How do I get to this big expression over here, given that I don't actually know what this function is? So I'm going to do the simplest possible thing. I am going to do a derivation of the one-loop tadpole from start to finish. This is going to illustrate the general methodology. And even though there are some twists and turns when you go beyond the one-loop tadpole, the general strategy remains the same. And for those of you that are familiar with how you derive differential equations in flat space, you're going to see that there are like a lot of analogies between the two. That basically it's really, I take very far this analogy where you replate the continuum with a discrete and everything follows the same as flat space. So here, this is the tadpole. What is the tadpole? It's a graph where I have a bunch of bulk to boundary propagators. I have n to bulk to boundary propagators. And I have one bulk to bulk propagator that starts and ends at the same point, gxx. The point here is that gxx is actually independent of x. So you can pull it out of this integral. So then now I'm just left with an integral over n bulk to boundary propagators. And this just becomes a contact diagram. And we know how to compute contact diagrams. So the non-trivial thing that we want to compute, or what the tadpole actually is that it's the bulk-to-bulk propagator where you set the end and the beginning at the same point. And you can, again, we know what this is. Like this is an example where we know how to compute this using other methods directly. But the point is that the strategy that I'm going to give you is applicable to graphs that to diagrams that we can't compute directly. So what do? We first use the so-called spectral representation of bulk-to-bulk propagators. So I've told you that the bulk-to-bulk propagator is a 2f1 hypergeometric function. That's very scary. It turns out that you can represent the bulk-to-bulk propagator as the product of bulk-to-boundary propagators. And bulk-to-boundary propagators are very simple. They're just 1 divided by x dot p raised to some power with some normalization. So this thing is like very, very simple. And the integrals are scary. These are what give you the 2f1 hypergeometric functions. But these are the integrals that basically we need to evaluate. So what you do is you take, if I give you a generic Witten diagram, the way that most people evaluate is they take all the bulk-to-bulk propagators. They break it into this representation. They do the integral over dq and the integral over x's. And then they need to do the actual integrals over c. And the integrals over c are the hard part, so to speak. You can do that with the tadpole here. If you do the integral over q for the tadpole and you set x equal to x prime, you get this nice function here, where you have this integral over dc, which is the same integral over dc that appeared here. You have this 1 minus c minus delta. This is kind of like the propagator. And then you have what we call the potential function w tadpole here, which is a product of gamma functions. You should not take this too seriously, but in my mind, I think of this as like the ADS version of like the Bykov representation. For those of you know what that is, it's like kind of a rough analogy here, where this like product of gamma functions is the ADS analog of the Bykov polynomial. So then now the goal is to compute this function. Note, it looks like an integral. That seems to go against the intuition that I've been telling you, because I've been telling you that you should think of ADS as discrete and flat space as a continuum. But this integral is secretly a sum over residues. So the sum over residues can be like, you compute it as a sum. So actually, this integral is really just a sum. So how do I compute it? I compute it the exact same way that I do in flat space. How do I compute the differential equation in flat space? I consider an extended family of integrals. So if I'm computing the tadpole in flat space, I don't just consider 1 over L squared plus M squared. I consider 1 over L squared plus M squared to the nth power. And this gives me a family of integrals. I do the same thing in ADS. In ADS, it amounts to replacing 1 over C minus delta with 1 over the Pockhammer symbol. This seems a little bit random. But the reason for that is that this Pockhammer symbol is directly analogous to 1 over x to the nth power. Because again, what is the defining property of 1 over x to the nth power? The defining property of 1 over x to the nth power is that if I take the derivative of 1 over x to the nth power, I get negative n divided by xn plus 1. That's what 1 over xn is really is. And that's what this inverse Pockhammer thing is. If I take the difference equation of the inverse Pockhammer, pi n, I get negative n pi n plus 1. So my claim is that this inverse Pockhammer is actually the direct generalization of 1 over x to the n when your system is discrete instead of a continuum. And this gives me a family of integrals / sums that's directly analogous to flat space. And what you can do is you can do the same exact thing in flat space. So in flat space, what I do here is I take my tadpole, I take the derivative of n squared. It gives me I2 from I1. Here I do the same thing. I take the difference equation in delta. It gives me negative I2, where this is the ADS version of this. But the problem here is that we need a second independent relation that relates I1 and I2 to actually write down a difference equation solely in terms of I1. And this is where summation by parts comes from. And again, integration by parts for ADS, for flat space, summation by parts because we now have a sum. So we write down the summation by parts identity for ADS, where it's basically the same way that you derive it in ADS, except for a sum instead of an integral. So in flat space, we derive integration by parts by considering a derivative inside the integral. Here, you consider it by taking a difference operator inside of the sum over residues. So this gives you a sum of INs that will give you some linear relation between them. And then in addition to that, you find the generalization of scalelessness. So there's a crucial property in ADS that if you're working in dimensional regularization, integrals that are scaleless vanish. So you have 1 over L squared plus M squared, where n is raised to a negative integer here, equals 0 in dim reg. This is a crucial property for those of you who've actually done IBP on your laptop in some class. You find a direct generalization of this in ADS. You find that the previous integral that I wrote down, if you take n to negative integer power, it vanishes. I say scalelessness in quotes here because ADS integrals aren't actually scaleless. You always have the ADS scale. So it's somewhat mysterious why these integrals are actually the scalelessness property remains and illustrates that it might be a deeper thing. But let's ignore deepness for the moment. It's just a useful property for deriving the difference equations. So here, I just repeat the procedure, and I get this nice summation by parts identity between I2 and I1. And then a note here for those of you that are curious, why is there this p prime here? The p prime here is a polynomial in C that's designed to cancel undesirable pole terms that come from when you act the difference operator on W tadpole. So now I have my two keys to the puzzle, so to speak. I have my difference equation in delta for I1 and I2 that relates I1 to I2. I have a summation by parts identity relating I2 and I1. I put them together, and I now have this difference relation acting on I1. And this should say d equals 1. So I have results that agrees with previous derivations of the tadpole. You can check that the tadpole actually obeys this difference equation. Ta-da. So we actually were able to derive the difference equation for the tadpole by effectively just doing some algebra without actually solving what the tadpole is. This is a somewhat trivial example because, again, we know how to compute the tadpole, but it's this strategy will generalize to more complicated integrals. So beyond the tadpole. So the next thing that we consider is the two-point bubble computation again. So before at the beginning of the talk, I considered the two-point bubble and specifically d equals 2. In d equals 2, the bubble is very simple. When you go to not d equals 2, it's very not simple. So the goal here is to now compute what difference equation the d not equals to 2 bubble obeys using the algorithm that I described before. And you repeat the same procedure. Now you have two integrals because you have two bulk edges. So you have this delta 1, delta 2, so you have 1 over C1, 1 over C2. And you find that the two-point bubble is proportional to the tree-level two-point bubble times this non-trivial function that you actually have to evaluate. So again, we repeat the summation by parts algorithm. I do a difference equation in C1. I have to insert this polynomial again to cancel undesirable pole terms that appear with WC1 plus 2. Here, I act the difference equation on this. I get some polynomial in C1 and C2 times the original factors, and then this gives me a sum that I can then, like, it just gives me, this now gives me a linear sum that equals to 0. Another identity that you need to use in the case of the 2-point bubble is the fact that if n1 is raised to -1 power, it collapses to a tadpole. This is, again, exactly analogous to flat space. In flat space, if I have my basis of integrals with ni, and one of the ni equals 0 or -1 or something, it collapses to a delta function. So one of your propagators just goes away. And it's the same thing here. If my tadpole collapses, if this propagator collapses, it just becomes a tadpole. So that's why you have this additional simplification that when one of the n1 is a negative integer power, it collapses to a tadpole. Then you can now derive difference equations in delta, proceeding in the same way. Again, there's a little bit of a subtlety here, because when you do shifts in delta of the w function, you can get undesirable poles. So you don't want to act the difference equation on just the original function, but again, insert a polynomial to cancel these poles. But in general, the algorithm proceeds as before. And you get this nice difference equation for the 2-point bubble for generic masses. You get similar results when you do the delta, when you do this difference equation for delta 1 and delta 2, and the result simplifies dramatically in d equals 2 to what I gave at the beginning of the talk. The results agree. There are further simplifications that this is somewhat unique to ADS that I can choose. Here you note that the I2 bubble only appears in 2 terms. I can tune my delta 1, delta 2, and big delta and h such that this term is equal to 0. So then I find that for those specific values, I2 bubble just equals some function times a tadpole. So for their very specific tunable values for which the 2-point bubble simplifies dramatically that I don't think were noticed before. You can then go and repeat this algorithm for the 4-point bubble in melon space. There is a new subtlety here, in that previously the w function was always a product of gamma function, and it's easy to see how the w function, if it's a product of gamma functions, behaves under difference equations. If it's not just a product of gamma functions, it becomes more complicated. So it turns out that it's nice to instead induce this auxiliary variable c, which I called c naught here, this should be c, which allows you to write down a w that's actually just a product of gamma functions. So this w here is just another product of gamma functions that I don't want to write down. And then you repeat the algorithm as before, where now you have a basis of n1 and n2, which correspond to like actual propagators in this graph, and this kind of auxiliary n equals that we want to set to eventually -1. Note that you only have scalelessness in n1 and n2. You only have this scalelessness property in the integrals that correspond to real edges. So here's an example of we derived the full difference equation for the 4-point melon bubble. I don't think this was known at all. We attached in some Mathematica files. So here we have a difference equation in the delta I. So this is the internal delta. And then this is a difference equation in the melon variable S. I attached a picture of one part of the Mathematica file. The one that's a difference equation in S, I think, is about 140 lines. I don't remember what the other one is. But note, this seems very complicated, but I've also kept everything completely generic. So this is a 4-point melon bubble where all the deltas are different from each other. If you set all the deltas to be equal, I expect some simplification to occur. So that's the talk. Future work. One thing that I didn't really talk about was actually solving the difference equations. You have an ambiguity technically up to a periodic function. There is hope here that some kind of physical input, such as a nice flat space limit, should be enough to actually fix the periodic function uniquely, but we weren't able to do that. There have actually been some results about solving the difference equations at tree level by using an ansatz, by using a particularly nice ansatz. But in general, this is just hard. Like, what physical conditions fix the periodic function? How do you solve the difference equations? Differential equations are hard. Difference equations are as hard, if not more so in some cases. Another future work is similar techniques should hopefully be applicable in de-Sitter. We have not thought much about this. I'm just noting this here. Please don't ask questions. And then finally, I think one state-of-the-art calculation that you could try to do is a triangle computation. So the 3-point triangle, even though it's naively one of the simplest things you could think of, is actually something that has not been evaluated in ADS, except for very specific choices of delta. So I can think of 2 examples off the top of my head where delta is conformal or delta equals d. So it's like massless triangle that it's been evaluated. But the triangle as a generic function of delta is has not been evaluated in any form. So just try, like, what's difficult here if you want to apply our method is that you need some more auxiliary integrals, just like the case of the 2-point bubble. But we expect the same computation strategy should work. I am funded by the Simons Foundation, to which I'm very grateful, and that's my talk.
Thank Aidan for a very nice talk. So we have time for a few questions. So maybe, or you're gonna ask? Okay.
I have a question, but I also have the mic, so haha. Is there any sense of how you might take these difference equations that you get algorithmically and put them in something analogous to an epsilon form?
No, it's as difficult as, like, that's a hard algorithm to do even for differential equations. Like, I suspect that these algorithms that use for differential equations should also be applicable, but I have not thought about it.
Thank you for your nice talk. I have a question. I know a triangle is very difficult, but I really want to know the box situation. So do you have any maybe small comments or?
That's going to be really hard. I know that the box has been evaluated for some specific choices of delta. I can give you a paper after the talk. I should have included it as a reference here. But doing the box for, I think my comment here with the triangle was doing the triangle for generic delta. If you're willing to restrict yourself to specific delta, then these computations become a lot more tractable if you restrict yourself to very, very special delta. In the same way that the bubble, I showed that the bubble like simplifies to gamma functions. If you'd made a very specific choice of delta and of your deltas here. So I expect something similar happens with the box if you make a very special choice of deltas.
Okay, thank you.
There's a question here.
So, I was wondering if you can go through the spinning guys by factoring some kind of a weight shifting operators on the.
Yes. Yeah.
That should be
that should be viable.
Okay. So the second question is when you take a flat space limit, like by taking variables to infinity, like do you recover the flat space results for these scalar integrals?
Do you mean for the difference equations or the integrals?
Sorry?
Do you mean for the difference equations or the integrals?
For the integrals.
Okay, I have not looked at that.
Yeah, I think there's 2 questions here. Maybe those are 2 last questions, I think.
But I know other people have.
So the genetic functions in space, there's or a SATA recurrence relations for recognitions. Is it the same that?
Are you talking about the tree level results? Like there's a tree level recursion for Mellon space amplitudes.
Talking about general hypergeometry.
Oh, okay. So you're saying recurrence relations for generic hypergeometric functions. Those will be a subclass of the relations we derive, I think. Yeah.
Okay, last question over there.
Hey, thank you for the nice talk. I know you said you don't want to hear about de Sitter, but I can do it in a way where you don't have to think too hard. In de Sitter, we have what we know is the principal series where for heavy fields, the deltas become complex. I was wondering if you have any concerns for this difference equation method when deltas could be complex.
I don't think it's an issue for when the deltas are complex. I think the issue is the contour. So before, like when you do integration by parts identities, even in flat space, the fact that you don't have any boundary terms in dim reg is a somewhat magical property. It turns out that this magical property generalizes in the way that we do it to ADS. But whether this generalizes if you pick the contours that are relevant for de Sitter is not something we've checked and not something that is like obviously true to me that will work. I wouldn't be surprised if it were true that if you didn't have any boundary terms in the summation by parts relations in ADS, but I think that's more the issue. Like these are analytic functions. Analytic continuation is not an issue. It's more that like you have to pick a different contour for de Sitter, and the different contour for de Sitter might be more subtle than the contour that we are working with for ADS.
Thank you.
All right, let's thank Aidan again.